In the previous video, we talked about sensitivity functions, and we said that the higher the value it is using this equation, the more sensitive it is, and therefore it is more easier to be disturbed by systems variations that could cause the system to be unstable. So it's not good. Okay, and therefore let's derive the sensitivity function. This is a transfer function that requires the response, or somewhat the reference that you take in, alright, and the disturbance and an input of a noise. So you have three inputs: the reference, the signal that you want, the disturbance, and the noise. And I'm trying to model this system so that we can actually deal with it and actually eventually minimize the number of disturbance and the noise that is actually distorting our responses. Alright, we have a filter over here, we have a controller over here, we have a plant over here. Alright, this this machine or whatever is over here. Okay, we have output over here. So now, normally when you want to do transfer function with this whole big chunk over here, you want to represent this whole equation in terms of the output, or in terms of a more simplified version. And therefore this is what we're gonna do right now. Alright, in order to solve for this transfer function, okay, I'll actually dissect the transfer function into three types. Alright, the first type is that I need, because there is three inputs over here. Alright, there's three inputs over here. Right, this is going into here, this is going into here, and this is going into here. So I'm trying to analyze in terms of inputs. Alright, and therefore I dissect the whole system in terms of input. And therefore, if I want to analyze the reference signal, I'll just ignore D of S. I so-called assume that they are not there. Alright, if that's the case, the transfer function for this system is the forward loop CP. Okay, in assuming that the filter itself is 1. Alright, so 1 times CP is just CP itself. Okay, so CP forward loop over 1 plus the forward loop feedback. Alright, so therefore I have CP 1 plus CP. This is the forward loop, this is the feedback loop. Alright, multiply with RS is equals to YS. So we actually write in terms of representing the output itself for the reference system. Now we talk about if we want to look for the disturbance. This is DS. Alright, this disturbance, therefore I will just ignore that there is existence of this thing anymore. There is nothing at all. There is no inputs over here also. And therefore I have a forward loop that straight away go to the output. This is therefore D of S 1 divided by a feedback loop that is going in this direction. And therefore we have 1 plus CP. Okay, and this equals to Y of S, because we are talking about in terms of output. Alright, so far so good. Next, the last one is the N of S. To analyze in terms of NS, I'll remove the existence of DS and RS, assuming that they are totally not there. Alright, and therefore the forward loop is simply going in this direction, because you can only go in this direction, right? You cannot like that go, like macam. So it does go in the forward loop. Alright, divided, so forward loop is actually simply CP. But take note, NS is the input over here, right? And then it goes through this summation point, which is minus. And therefore we have a minus N over S over here. And then divided by the feedback loop is simply feedbacking again. Alright? So it's just 1 plus CP. That's all. This equals to Y of S also. And therefore I've represented this the transfer function into three types. And the whole transfer function in terms of the three so-called, imagine if you have a therefore I can re-represent this transfer function, or sorry, this block diagram in terms of this tree, as I've proved to you earlier, right? So therefore it's just a summation of all these things. Alright, if I were to do that, alright, therefore I'm simply taking the reference, the disturbance, and the noise, and sum them up together. And therefore I'm just simply taking this stuff, I'll just paste it over here, this stuff, I paste it over here, this stuff, I paste it over here. Alright, now I'll just move all this stuff over here. so that it's better represented. Alright, so I will not cheat your feeling. It's all over here, right now. Okay, I'll just move it over here, right here. It's equals to n of s, and just clear away all this. Okay, and then plus. Now this is the whole system to represent the output. Okay, and CP1 over plus 1 over CP over 1 plus CP is, we call it the complementary. To introduce 1 over 1 plus CP first. If you take a look, 1 over 1 plus CP is simply our sensitivity function. Alright, so therefore I've derived the sensitivity function over here for you. Okay, and therefore I can say that this is S, and this CP over 1 plus CP, and this is also CP over 1 plus CP, is simply T, and we call this the complementary sensitivity function. Alright, complementary is like one, you buy one get one free lah. Okay, I don't know any meaning actually. So this is something that I really don't know. Alright, I really don't know this. And now we have another don't know where the hell comes from. It is that T plus S is equals to 1. Alright, I don't know where the hell it's come from, but it comes from somewhere, and when I find, it's actually over here. Control nodes, P2 feedback control, this is the name, and something that talk about S plus 1, but it's gonna deal with really a lot of things. I don't know where do I start from, but I can actually read it up if you're free. So this is a recommendation for S plus T equals to 1. Okay, now what is actually T and S? What are actually the trend of T and S? Okay, trend of T and S is simply CP and 1 plus CP, right? But what actually are the trends of its behaviors in terms of responses? Alright, so I'm just gonna paste it here. So T is in fact this one, S is in fact this one. Now, in order to observe its behaviors, I'm gonna ensure that I define what is CP. And CP, if you remember, actually, if you close loop it, you're gonna actually create a Nyquist plot. Right? This is a Nyquist plot, real and imaginary. You're gonna see whether things are negative, gonna go -1 or things like that. So this transfer function, in this case, I'll keep it simple. I'll say CP is equals to, you can just define CP as some transfer function K over AS plus 1, where CP is simply a controller and a plant. That's all. Going is just an open loop CP. Okay, so we're analyzing in terms of the open loop system. Open loop. Okay, to define as OL over here. It's not office lady, open loop. Okay, AX is equals to J, where S is equals to J omega. Right, if I were to do that, then what can I see from here? Okay, so I'll just sub it in. Sub it in, I'll have all these things out already. Okay, but now, so is this. Okay, now I'm gonna rearrange because it's kind of very very messy. So I'm gonna multiply in terms of AS plus 1 to this whole equation over here. Alright, so this thing is in fact just 1, so I'm just simply multiplying 1 into this equation, that's all. So with this set, alright, so therefore I'll just cancel, and then I'll multiply 1 as AS plus 1, and then this one cancel, this one multiply in, and then this one multiply with 1, and then cancel with this, cancel. I think you get what I mean. It's just simply rearranging. So at the end of the day, what I have is just this one. Okay, plus AS plus 1. Okay, so therefore we have this. Alright, so we didn't actually change the trend of T plus S is equals to 1. Alright, because if I were to change, then currently if I were to prove to you right now, alright, if this thing plus this thing, what do we have? It's simply AS plus K over AS plus K, alright? And you see they are the same form, right? So I can cancel each other, become 1. That's all. Alright, so therefore I didn't change anything. I'm just simply rearranging them. I'm simply rearranging them. So now I have this transfer function over here, or this equation over here, for simplicity's sake. So this thing is simply still for S. Alright, sorry, it's for T. is for the complementary transfer function. Alright, although yeah, it's for this one. S is still this one, so I'm just simply rewriting everything for clearest sake to prove to you a certain trend for the response. Now, because S is equals to j omega, so we can actually assume that if S is equals to infinity or equals to j infinity in this case, alright, because omega is simply you get what I mean? So if omega equals to infinity, it is j infinity, and therefore S is equals to infinity. You just pause the video and then you get the meaning. Okay, if S is equals to 0 is equals to j times 0, we can say that omega is equals to 0, or in other words, I'm talking opposite. If omega is infinity and 0, then we have all this. That's what I mean. Okay, so I'm going to prove to you that along these frequencies, how does S and T behave? And at the end of the day, you should know that they're actually low pass and high pass. Okay, one of them. So if I were to put inside, this is actually T, the complementary, and this is the sensitivity function. And what we can do is, if that's the case, then what can you see? Alright, we can see that k over infinity plus 1 plus k, because I'm just simply subbing S as infinity. So it's just a infinity, but anyway. So if this thing is, this whole denominator is infinity, then the number divided by such a big number will become 0. For this whole thing becomes 0, plus, alright, this is simply as plus 1, I'm just rewriting. And therefore, a infinity, alright, so if you were to cancel, a infinity plus 1 is same as a infinity plus 1. So in this case, I can just say that it's infinity over infinity plus k. That's all. Alright, I'm just simply rewriting this thing as infinity, because infinity is some arbitrary large, super big number. And infinity, because it's, for example, 1000, for example, if k is just 2, so 1000 divided by 1000 plus 2, in this case, is equals to 0.99. And if round off is equals to 1, we are still sufficing or satisfying the equation itself, and therefore it's okay. Alright, therefore if you want to look at the response, alright, we have a graph containing omega and the gain, alright, the gain. And therefore at high frequency, which is super high infinity, you're gonna have a 1 over here. So we are talking about high pass frequency. So T is in fact a high pass frequency. Alright, so we have proved that T is equals to high pass frequency. And therefore using this same method of derivation, because I see that there's no point in deriving when S is equals to 0, because it's straightforward, it's same as what I've derived. But I just want to convey that the graph itself, in this case, is a low pass. Alright, you just need to know that at frequency is equals to 0, you have equals to 1. Alright, you have a 1 over here. And when high frequency, infinite frequency, you have 1 over here. That's the meaning of that. Alright, that's the two meanings of that. I'm not going to derive that, but since you know this will come naturally. Okay, and therefore this S is a low pass frequency, because it pass low frequency in. You see, low frequency range, it has a gain of 1, for example. Alright, and for high pass frequency, if you have a very high frequency, you have a 1 magnitude gain. That's all it is. Alright, now let's come back here, since we know the full understanding of how this S sensitivity function works. Okay, that why is it max? Why do we interested in max? If you still remember, the sensitivity function is in terms of a Nyquist plot that is very near to -1, which is gain margin and phase margin is in fact very high. This means that they are stable in terms of gain and phase, but however in terms of sensitivity, they're actually very near to -1. Alright, so when we know it is very high, then we can straight away know that it's dangerous. And when we know that straight away it's dangerous, and we can pick up its frequency from 0 to infinity, because this one, this side over here is totally mirrored with this side. So this is from 0 to infinity. This is from 0 to minus infinity, right? It's going this, it's going, sorry, it should be from 0 to minus infinity. So they are just mirror each other. So I'm just taking 0 to infinity will do. Alright. What I want to convey is that at this frequency, at this certain frequency here, we have as the sensitivity, alright, J omega is equals to very high number. Alright, very high. If you were to plot into the body plot, there will be some frequency and then it will be a spike over here. And this spike corresponds to this position over here. And this means that there is some, because, okay, this body plot is in terms of frequency and gain. Okay, so there will be a very high gain over here, a spike suddenly. Alright, and therefore we want to remove the spike. And since we know that this gain is very high and we can know straight away which frequency we are using in terms of the max value of the sensitivity function, then we can implement a notch filter. Alright, a notch filter is simply to remove the spike. Alright, so in other words, a notch filter, if you were to take a look at this body plot, is simply like this. So at this certain frequency, it actually cut off. So you actually remove that certain frequency. So if I were to implement this thing over here, at the end of the day, I'll actually cut off this frequency, and my outcome would be something somewhat like that. I don't know, but at least it's more stable. Okay, this graph may not be correct, but at least we convey that we can remove the spike. So when we input the notch filter, this means that we're going to alter the transfer function of CP. We're going to add maybe 1 over s plus 1 or things like that, I don't know. But this is just the concept of why we're talking about max and how it's being applied. Now, let's come back to here. I know that I'll keep jumping here and there, but anyway, we know that T is high pass. Alright, when it's high frequency, it actually allow a gain of 1. That means a full gain. At low frequency, then you allow a gain of 1 over here at S. So in this case, low frequency, S is equals S plus T is equals to 1. And therefore, at low frequency, alright, if you take a look at low frequency or perhaps low frequency, S is equals to 1 plus T at low frequency is in fact 0. So it's the full power of S. And as for high pass, S plus T equals to 1. If S, alright, if you take a look, S, in this case, infinity, if let's say this point is infinity, at infinity frequency, this S is equals to 0, right? The gain, you see, the gain is in fact 0. And then T at this point is actually gain of 1. So T is equals to 1. Alright. So as you can see, this trend, although we can represent T equals to 1 and S equals to 1, but we are trying to dodge it. We want T and S to be maximum 1. Alright. But I do not know much of the reason. I decided to come to this part over here. This is the one that we derive from our transfer function, our block diagrams, right? We break them down and eventually I have this one over here. Now if I were to sub in as low frequency, if it's a low frequency, this means that S is equals to 1, right? Because it's a low pass, as we can see over here. Low pass, S is equals to 1, and T is equals to 0. And therefore, as you can see, T will become 0, this one will become 0, and therefore, it's a full power of S. Alright? And therefore, it's a full power of disturbance. You have a lot of disturbance that is going to occur. This part, I do think that I have understand. But if we're talking about if high frequency, then distance will be 0. You have no disturbance, which is very good, You're only gonna minimize the noise over here, alright, or you're gonna minimize the transfer function over here. So this transfer function that's shared between RS and NS is CP over 1 plus CP. So they actually share the same transfer function or share the same T. So T is maximum, so we're just trying to solve for the N of S, we're trying to minimize it, and that's it. Right? That's the key reason. And we can actually minimize the transfer function also, but why don't we want to take a high frequency and set this to 0 and work in terms of the noise, and then we can get a full response of it. I don't know the reason why, but just to take away is that t plus s must be equals to 1, and that's all. Alright, and never that t and s never is 1 or near that. It's some ratio between them. Maybe this is 6, this is 4, this is 7, this is 3, something like that. Okay, I don't know, but this is something that I really don't know. And therefore this comes to the end of my this video. This is the list of the what I know, what I don't know, and recommendations that I have. I'll paste it inside the comments below. And yeah, next video.